Hey everybody, before we jump into this historic result about Fermat numbers, I want to briefly talk to you about the relationship between the divides operator and then congruence. 6 divides 30 means that 6 is a divisor of 30, and it certainly is because 30 is equal to 5 times 6. But you can also write this equivalently, denoted by the double arrow, or by the arrow here. You can write this 30 is congruent to 0. And there's a very brief primer on modular arithmetic, and this is mod 6, modulo 6. That's abbreviated, mod 6. Now, another way of understanding what the 0 is all about is note that 30 upon division by 6 leaves a remainder of 0. So 30 is equal to 5 times 6 plus 0. And sometimes modular arithmetic is called remainder arithmetic for this reason. And again, this number right here is called, it's a huge number obviously, 2 to the 32nd plus 1. I believe it's about 10 digits. This is called a Fermat number. And this number right here is actually called F5. And the reason is F's for Fermat, the famous lawyer mathematician. And notice this is 2 to the 5th right here. This is 32, the exponent is 2 raised to this 5th power, you see. And I believe Fermat conjectured that 2 to the 32 plus 1 was prime. 100 years later, Euler comes along and proves that 641 is a divisor, meaning that F5 is not a prime, but a composite number. Now, again, I never would have discovered this, but I know that just from reading the history books on math, that 641 is a divisor of this big number, and I want to show you why that's true via modular arithmetic. Okay, now, per this example, hopefully you'll agree that the problem statement is absolutely equivalent to the quantity 2 to the 32nd plus 1 being congruent to 0 mod 41. And the nice thing about this triple arrow, this congruent symbol, is you can treat it like an equality symbol in a lot of cases. All right, now let's get started. So here's our 2 to the 32nd plus 1. All right, now we rewrite it like this for a not so obvious reason. You wouldn't know if you hadn't played around with the arithmetic here. But 2 to the 14th, or excuse me, 2 to the 4th is equal to 16, right? But notice that that is congruent to minus 625. And y'all, this would be mod 641, of course. That's the... Okay. Y'all, one way to think of this is think of this as subtraction, sort of, and you go 16 minus whatever this is a multiple of the modulus. Well, it's exactly equal to the modulus, so that also counts as being congruent. You can be equal, or 21 is congruent to 14 mod 7. They're not equal, but they both are multiples. They're both multiples of 7. They both leave remainders upon division by 7. But notice that this is equal to, also equal to, minus, and you are not raising the 5. I mean the minus to the 4th power, but that's minus 5 to the 4th, right? So that's exactly why we can replace 2 to the 4th right here with minus 5 to the 4th, and take care to not think of this as minus 5 quantity to the 4th. It's not. 2 to the 4th is congruent to minus 625, but that turns out to be minus 5 to the 4th. So this minus is not getting turned into a positive, okay, because of the even power. Okay, so that's, notice how I use equality here, but this is a congruent statement because I replaced 2 to the 4th with what it's congruent to, modulo 641. And the rest of this is all modulo 641. I'm not writing it down, okay? Now, y'all, I didn't do too much on this next step except drag the minus sign out front, right? Okay, I dragged the minus sign out front. Notice I use an equal sign because this is just laws of exponents here, okay? This is just laws of exponents, so no congruent stuff happened. You have two objects raised to the 4th power, so you can combine them like this, right? Standard, just laws of exponents, okay? a to the b, a to the m times b to the m is equal to a times b to the m is the rule if those are the letters you like. Okay, now, oh no, what do we got here? We have this minus 1, right? Well, notice that 2 to the 7th times 5. And again, you have to, I fumbled around with this well before this video, and that's how I knew it. It's no way you just walk through this and know to even start with this step, right? Okay, but this is 640, right? But notice that's also very conveniently, and I don't think Euler saw this, or maybe modular arithmetic wasn't super prevalent back then or even fully developed, I don't know. But this modulo 641 again, folks. I'm leaving the modulo, but everything's mod 641, so I'm avoiding the clutter. So 2 to the 5th is 128. 5 times 128 is 640. And 640 minus a negative 1 is 641 itself, which is certainly a multiple. A number is a multiple of itself, right? So do you see how this entire thing gets replaced with negative 1 right here? Okay, isn't that cool? This negative 1 that you see here is negative 1, right? So this is congruent. Now we can to 0. That's equal to 0, and we can also say congruent if we want to. So that's congruent to 0, mod 421. Mod 641. Y'all, and that's it's QED time. Thus we've demonstrated quandam est demonstrandum, or something that's no longer pronounced these days. So we're finished, folks. And I thought that was super cool because, again, you don't even have to know how to pronounce 2 to the 32nd plus 1. It's a huge number. We don't even know what its Hindu Arabic rendition is. I don't know, and I don't care. Not important. We were able to establish that 641 is a divisor of the 5th Fermat number. And I like it quite a bit. It just shows you how incredibly powerful modular arithmetic can be. Notice the biggest number we had to calculate was 2 to the 7 times 5. But you had to know that just to write it this way. Don't think, oh, you could have written this as raised to the 4th to the 8th, right, or something. But it just turns out knowing these various specific case numerical examples helps you. But they're smaller numbers than the 10-digit numbers you would run into if you tried to, which is, I think, how Euler did it. He actually knew what this number was, Hindu Arabic, even though they didn't call it Hindu Arabic then, I don't think. And he went through it and figured out, was it Euler, I guess, I don't know what I said, but Euler figured out that 641 was a prime when a century before Fermat speculated or conjectured that this was prime. And the latest on these Fermat numbers, the first 4 are prime. F to the 3rd, I think, is 257. One of them is 120. Well, I'll just write them down for you. F cubed, or not, F sub 3, excuse me, is equal to 2 to the 2, like that. See, that's what a Fermat number is, F sub 3. Okay, so this would be 2 to the 8th. So this is 257, right? So this is prime. Okay, this is a prime number, and F4, I believe, is also prime. But F5 is not prime. We've just demonstrated that F5, a Fermat number, is not prime. And the old number theory books say that it's still not certain if there's any other prime Fermat numbers, but the current stuff seems to lean towards the fact that F1, F2, F3, and F4 are the only prime Fermat numbers. I don't think it's been proven, but there's strong speculation or conjecturing that that's the case. But anyway, I hope you enjoyed that. I hope it helps you see how potent modular arithmetic can be. Okay. All right. Thanks for viewing.